Welcome to Code Along with Alex. I'm Alex, and today we're jumping into Julia, so let's get started. We're going to pick up where we left off last time, except we're going to use the Jupyter Notebook experience instead of just typing directly into Terminal. So let's get going. Today we are looking at complex and rational numbers. At least to start, we're going to go through a few sections, so don't worry, get a little more exciting. But I'll create separate notebooks for each section, so just to keep things separate. And let's get going. Okay, cool. So Julia includes predefined types for both complex and rational numbers and supports all the standard mathematical operations and elementary functions on them. Conversion and promotion are defined so that operations on any combination of predefined numeric types, whether primitive or composite, behave as expected. And so before I go any further, this is directly from the Julia language manual, and I will link this in the video description. And if you're here live, it's in the Discord chat. Great. So to start, we'll look at complex numbers. The global constant I am is bound to the complex number I, representing the principal square root of -1. Using mathematicians I or engineers J for this global constant was rejected since they are such popular index variable names. Yeah, that's true. Since Julia allows numeric literals to be juxtaposed with identifiers as coefficients, this binding suffices to provide convenient syntax for complex numbers, similar to the traditional mathematical notation. Okay, so we just looked at IM. This is straight from the docs, but 1 plus 2 IM. Okay, it just prints that out. Let's do a little arithmetic. So 1 plus 2 IM divided by 1 minus 2 IM. Rad. Okay, so Julia does complex number arithmetic. That's cool. Can we do like exponential stuff? I mean, like, yes, but like let's take a look. And then raise this to 1 plus 1 IM. Interesting. Okay, very cool. I think that's enough complex number arithmetic for me for today. And then the promotion mechanism ensures that combinations of operands of different types just work. Okay, so let's take a look. It's kind of similar to what we just did, but yep. And then 3IM divided by 2. Okay, so things just work. Great. Okay, and then standard functions to manipulate complex values are also provided. Nice. Okay, this is where it gets a little more interesting. So let's define z equals 1 plus 2IM. Let me add some spaces to increase readability. And then we can, I guess, use the real function to just return the real part of this complex value. So we'll just do real. Will this work? Real z? Yeah. And then if you do imag z, let me spell that right, you get the imaginary part of z also. So that's pretty cool. Also stuff like absolute value squared. We're not going to go through everything. But yeah, you get the idea. It's some nice built-in mathematical functions if that's what your application requires. And if you're using Julia, it probably does, because otherwise you could likely use some other language that might not be as mathematically inclined. Okay, and then as usual, the absolute value of a complex number is its distance from zero. Abs2 gives the square of the absolute value and is of particular use for complex numbers since it avoids taking a square root. Angle, yeah, that's true. Angle returns the phase angle in radians, also known as the argument or arg function, and the full gamut of other elementary functions is also defined for complex numbers like square root, cosine, exponential or exponent, sine. Okay, very cool. And then mathematical functions typically return real values when applied to real numbers, and complex values when applied to complex numbers. So square root behaves differently when applied to -1 versus -1 plus 0 IM, even though -1 equals -1 plus 0 IM. So let's take a look. So square root, -1. It's thinking, yeah, error, okay. And then what about square root -1 plus 0 imaginary? Interesting. So you can see it's a different behavior even though it's the same function and technically the same value, but you're kind of overriding that behavior by passing the secondary zero coefficient imaginary component. Sweet. Okay. Going a little more into imaginary kind of power user stuff, but let's... And then infinity and NaN propagate through complex numbers in the real and imaginary parts of a complex number is described in the special floating point value section. Okay, so we'll come to that in a bit. But yeah, you can interact with infinity, NaN, and it just kind of propagates as such, where 1 plus inf times im, and it's just kind of the infinity propagates. Okay. Let's move on to rational numbers. Let me actually add an additional label just to keep track of stuff. So, complex numbers. Ooh. Using some Markdown, which is the nice part about Jupyter Notebooks. You can embed Markdown quite easily and do some sophisticated report style writing. But yeah, let's move on to rational numbers. My main experience using Jupyter Notebook is in the context of Python, so it's cool to try a different language with Jupyter Notebooks. So rational numbers. Julia has a rational number type to represent exact ratios of integers. Rationals are constructed using the / operator as such. Nice. If the numerator and denominator of a rational have common factors, they're reduced to the lowest terms such that the denominator is non-negative. Okay, let's see that in practice. Okay. What if we make the denominator negative? It's -15. Okay. That's what it's expected. Great. This normalized form for a ratio of integers is unique, so equality of rational values can be tested by checking for equality of the numerator and denominator. The standardized numerator and denominator of a rational value can be extracted using the numerator and denominator functions. That's pretty cool. Numerator 2, 3. I'll copy paste that because I'm a little lazy. Nator. Nice. Okay. Impressive. And the direct comparison of the numerator and denominator is generally not necessary, since the standard arithmetic and comparison operations are defined for rational values. So let's do a couple comparisons just for the heck of it, but we won't do too many. It's not the most exciting. Very cool. Okay, let's do one with non-comparison. Let's do multiplication. Nice. I like it. It's convenient. And then you can easily convert a rational to a float using the float keyword if you spell it right. Nice. And then conversion from rational to floating point respects the following identity for any integral values of a and b, with the exception of the case a equals 0 and b equals 0. So an example would be like a equals 1, b equals 2. I'll just separate the lines. Okay, make sure a is in, yep, okay, is using the is equal function. We can check if the float version of a literal b or rational b is the same as a divided by b. And it's true. Okay. And you can also construct infinite rational values. It's acceptable. Like so. Okay. But constructing a not a number rational value is not valid. So this is not cool. Not chill. Okay. And then the promotion system makes interaction with other numeric types effortless. Very nice. So let's see a couple examples. Times 0.75. Very nice. 5 divided by 2 plus 3im. Actually, let me add some parentheses. PEMDAS. Ooh, nice. Okay, that's cool. And that's it for complex and rational numbers. So now let's move on to a new Jupyter Notebook. I'm going to save this, close this, create a new file in this directory called, what are we doing next? Ooh, we're moving on to strings. Okay, strings.ipynb. Let's change the runtime to Julia. And then let's create a markdown cell to just add a little bit of context for our project. So we'll call it, and this is all using markdown, strings. Let me copy paste some of the info I had from the previous one just to save some time. Okay. So this we'll call strings. And then we'll update the Julia manual link to be the URL for strings, and then we'll shamelessly promote my YouTube channel. All right, cool. So let's delete this markdown. Oh, should have left it. Okay. Actually, yeah, we should have left it. So let's go. So strings are finite sequences of characters. Of course, and this is all again from the tutorial link here, and that's going to be shared in the video recording as well. So let's go going. Strings are finite sequences of characters. Of course, the real trouble comes when one asks what a character is. I feel like I'm a character, you know what I mean? But that's not what we're talking about. The characters that English speakers are familiar with are the letters A, B, C, etc., together with numerals and common punctuation symbols. Yeah. These characters are standardized together with a mapping to integer values between 0 and 127 by the ASCII ASCII standard. There are, of course, many other characters used in non-English languages, including variants of the ASCII characters with accents and other modifications, related scripts such as Cyrillic and Greek, and scripts completely unrelated to ASCII in English, including Arabic, Chinese, Hebrew, Hindi, Japanese, and Korean. The Unicode standard tackles the complexities of what exactly a character is, and is generally accepted as the definitive standard addressing this problem. Depending on your needs, you can either ignore these complexities entirely and just pretend that only ASCII characters exist, or you can write code that can handle any of these characters or encodings that one may encounter when handling non-ASCII text. Julia makes dealing with plain ASCII text simple and efficient, and handling Unicode is as simple and efficient as possible. In particular, you can write C-style string code to process ASCII strings, and they will work as expected, both in terms of performance and semantics. If such code encounters non-ASCII text, it will gracefully fail with a clear error message rather than silently introducing corrupt results. When this happens, modifying the code to handle non-ASCII data is straightforward. Okay, we're getting there. Some bullet points, and then we'll get into code, so bear with me. But this is important stuff, and I know some people don't like to read, so I'll read it for you, and hopefully you'll listen to this. There are a few noteworthy high-level features about Julia strings. The built-in concrete type used for strings and string literals in Julia is string with an uppercase S, as such. String. This supports the full range of Unicode characters via the UTF-8 encoding, A transcode function is provided to convert to from other Unicode encodings. All string types are subtypes of the abstract typed abstract string, and external packages define additional abstract string. Ooh, that's tough to say. Subtypes, e.g. for other encodings. If you define a function expecting a single argument, you should declare the type as abstract string in order to accept any string type. Like C and Java, but unlike most dynamic languages, Julia has a first-class type for representing a single character, called abstract char. The built-in char subtype of abstract char is a 32-bit primitive type that can represent any Unicode character, and which is based on the UTF-8 encoding. As in Java, strings are immutable. The value of an abstract string object cannot be changed. To construct a different string value, you construct a new string from parts of other strings. Okay. And then conceptually, a string is a partial function from indices to characters. For some index values, no character value is returned, and instead an exception is thrown. This allows for efficient indexing into strings by the byte index of an encoded representation, rather than by a character index, which cannot be implemented both efficiently and simply for variable width encodings of Unicode strings. That was a mouthful. Okay. Now let's move on to characters. So let's actually add a Julia cell. Okay. So a char value represents a single character. So C equals X. Yep. It's just a 32-bit primitive with a special literal representation and appropriate arithmetic behaviors, and which can be converted to a numeric value representing a Unicode code point. Julia packages may define other subtypes of abstract char, e.g. to optimize operations for other text encodings. Here's how char values are input and shown. So we put in that C char. Let's now return the type. Thrilling. Type not defined. Oh. Apologies. Type of. It's kind of slow, to be honest. Okay. You can I've heard that Julia is kind of slow to compile, but I guess, yeah, because we're doing this interactive mode, it's a little different. So just running each cell is like recompiling the whole program. Okay, interesting. But this is good for just iteration or just learning and kind of more exploratory tinkering. Okay, so you can easily convert a char to its integer value, i.e. code point. So let's do C equals, so we're overriding our initial binding, the integer representation of the character X. And then let's do type of C. Nice, integer 64. And then on 32-bit architectures, the type of C will be int32. That's just like a note to self. And then you can easily map back to the char type from integer, which is cool. Not all integer values are valid Unicode code points, but for performance, the char conversion does not check that every character value is valid. Okay. If you want to check that each converted value is a valid code point, use the isValid function. So let's create an invalid character and see what happens. So this is our invalid character. Yeah, it's too high. Okay. So now let's use the isValid function. Pass the char type. And then again, our value. And then we'll see that it is not valid. Okay. As of this writing, which is the November 5th, 2022 that I'm reading this. As of this writing, the valid Unicode code points are U plus 0000 through UD7FF and U plus E000 through U plus 10FFFF. These have not all been assigned intelligible meanings yet, nor are they necessarily interpretable by applications, but all these values are considered to be valid Unicode characters. And you can input any Unicode character in single quotes using the \U followed by up to 4 hexadecimal digits, or \U followed by up to 8 hexadecimal digits. The longest valid value only requires 6. So an example of that, let's see the \U0. And then I'm going to copy that just to save a little time. \U2200. Nice. And so you can see it's a different type of Unicode category. Thrilling. And then an example of one that is yet to be assigned is U10FFFF. And that should be an uppercase U. And you can see it's other, not assigned. Wild. Okay, so Julia uses your system's locale and language settings to determine which characters can be printed as is, and which must be output using the generic escaped /u or /U input forms. In addition to these Unicode escape forms, all of C's traditional escaped input forms can also be used. I'm gonna skip that, but yeah, just go to town with escaping your input strings. And you can do comparisons and a limited amount of arithmetic with char values. It's using your chars, not your input strings, your input chars. So let's just do a comparison of chars and move on to strings. So A less than A. Weird. And then A plus 12. Weird, but it makes sense in a way. Okay. That was our whirlwind tour of char type. Let's move on to string basics. So let me create a markdown cell to denote that we're moving on to a different section. Cool. So string literals are delimited by double quotes or triple double quotes. What's up, Shittabem? We're just jumping into string basics with Julia.
Hey, Parker.
How are you?
Can you hear me?
Yeah. Can you hear me? Can you hear me now? Hello.
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 Can you hear me, Parker?
Yeah, can you hear me now? Hello.
Yeah, I can hear you now.
Okay, cool. I forgot to turn on the voice activity on Discord because I'm alone. So I'm just recording, but like
Yeah.
I have audio on the OBS, but then I forgot to turn it on Discord because no one told me yet. But yeah, how's it going?
Oh, man, I'm okay. Yeah, I'm not feeling too well. I'm a bit down. Uh, I'm a bit ill. So, uh,
Damn, you should go to bed, dude.
but yeah, I'm fine. Yeah. I just wanted to jump in and
Oh,
say
for
hello
sure.
before I jump off.
Okay, cool. Well, yeah, no, thanks for saying hi, and
Yeah,
I hope you
yeah,
feel better soon.
yeah. I would watch the recorded session. I hope to join you on the Rust sub streams on Monday.
Oh, sick. Okay, cool. Well, that'll be exciting. Yeah, I'm gonna try to do more weekday content so people can join. Yeah, but yeah, hope to see you there. But yeah, feel better.
All right.
Bye.
Thanks, man. Uh,
All right, let's get back into string basics now. That was Chidibim, another advocate and DAO member from Graph Advocates. So that was cool, little cameo. He's feeling under the weather. So let's send some positive vibes to Chidibim. So hopefully he feels better soon. So let's do string hello world. And then throw in a new line at the end. Nice. And then you can also do a little more aggressive. Contain, not aggressive, but just like lots of quotes. So using triple quotes, and then you can embed single double quotes. And then you'll see how that is returned as such, which is nice. And then long lines and strings can be broken up by preceding the new line with a backslash. So let's create another variable called long string equals, this is a long line. Nice. And then if you want to extract a character from a string, you index into it. So let's take our long string. And then str. Actually, no. Long string begin. Ooh, t. Okay, so the first indexed values begin. Can you also do 0? Just coming from other programming languages, that's more what I'm used to. Oh, interesting. Oh yeah, it's one indexed. Weird. Okay. Yeah, I guess it's one index, so you can use one or begin. And then you can also use the end identifier, which is cool. Yeah. All right. Many Julia objects, including strings, can be indexed with integers. The index of the first element is returned by first index str, the first index function. And the index of the last element character with last index str. Nice. And that would be like first index long string, and last index long string. Very cool. And then you can also do simple arithmetic on your index values like this. So we'll take last index, or no, we'll take long string, and we'll do begin plus 3. And you can see how we're traversing the index using simple arithmetic. And then you can also extract a substring using range indexing. So that's kind of cool. So we'll do long string. We go 3 to 10. Is a weird. About 1. Oh, this is I was like, why is there 2 is's? Okay, cool. And then notice that the expression strk and strk:k do not give the same result. So that would be like long string 5 returns a different result than long string 5:5. Interesting. This version is a single character of type char, while this one is a string value that happens to contain only a single character. In Julia, these are very different things. Nice. Okay. And then range indexing makes a copy of the selected part of the original string. Alternatively, it's possible to create a view into a string using the type substring. Let's try that. So we'll do sub str equals substring. Oh. Substring. And then we'll do long string. And then we'll pass 4 through 11. Nice. And then let's do type of sub str substring. Very cool. And several standard functions like chop, chomp, and strip return a substring. All right, let's move on to, I guess, Unicode and UTF-8. So let me create another markdown cell. Save the file. Avoid catastrophic data loss. And let's get going. Let me take a sip of some water. Stay hydrated. Okay. So Julia fully supports the Unicode characters and strings. As discussed above, in character literals, Unicode code points can be represented using Unicode /U, uppercase and lowercase, escape sequences, as well as the standard C escape sequences. These can likewise be used to write string literals. So let's try to type this out without messing up. It's a little tough sometimes. That's okay. So we got U2200 X U2200 or 2203 Y. And let's see what that returns for us. Oh, fancy. Whether these Unicode characters are displayed as escapes or shown as special characters depends on your terminal's locale settings and its support for Unicode. String literals are encoded using the UTF-8 encoding. UTF-8 is a variable width encoding, meaning that not all characters are encoded in the same number of bytes. Code units. In UTF-8, ASCII characters, i.e. those with code points less than 0x80, 128, are encoded as they are in ASCII using a single byte, while code points 0x80 and above are encoded using multiple bytes, up to 4 per character. String indices in Julia refer to code units, bytes for UTF-8. The fixed width building blocks that are used to encode arbitrary characters, code points. This means that not every index into a string is necessarily a valid index for a character. If you index into a string at such an invalid byte index, an error is thrown. So we have S. Let's do S at index 1. Okay, we have that upside down A thing. Sorry, I don't know the actual name for it. You can see at 2, we don't have anything going on, which is interesting. So it's an invalid byte index. But then if we do S of 3, what happens? Same thing. But S of 4. So that's valid. Weird. Okay. So the character upside down A is a 3-byte character. So the indices 2 and 3 are invalid. So it has to do with how much space it's taking up. Okay. And the next character's index is 4. This next valid index can be computed by next ind S1. So that would be next ind S1. 4. Okay. And then you could do and so on and so on. Since end is always the last valid index into a collection, n-1 references an invalid byte index if the second to last character is multi-byte. Okay, so let's do Sn-1. Let's do Sn-2. Yeah, okay. Invalid nearby indices. Okay, so the first case works because the last character y and the space are 1-byte characters, whereas n-2 indexes into the middle of the backwards uppercase E multi-byte representation. The correct way for this is using the prevind method, or if you're using that value to index into S, you can write another prevind statement. So let's try that. So S previous ind, I guess. Yeah, prevind. Previous index, S end, and then 2. Nice. So we're not worrying about, or it kind of circumvents that string index error. Very cool. And so extraction of a substring using range indexing also expects valid byte indices, or an error is thrown. Oh, okay, so this is where things start to get a little tricky. So if you do S1:2, okay. But then S1:4, damn. Okay, so because of the variable length encodings, the number of characters in a string given by length S is not always the same as the index. If you iterate through the indices 1 through last index of S and index into S, the sequence of characters returned when errors aren't thrown is the sequence of characters comprising the string S. Thus, length of S is less than or equal to last index of S, since each character in a string must have its own index. The following is an inefficient and verbose way to iterate through the characters of S. Let's do it. For I equals first index of S through last index of S, try print ln. Ooh, I'm doing Rust right now too, so it's weird doing the println. I'm used to it having the exclamation point. Okay, catch, and then we'll just ignore the index error and end. So let's run this cell. Nice. Okay. The blank lines actually have spaces on them. Fortunately, the above awkward idiom is unnecessary for iterating through the characters in a string, since you can just use the string as an iterable object. No exception handling required. Dope. For C and S, no. Print ln C end. Yo, that's cool. If you need to obtain valid indices for a string, you can use the nextInd and prevInd functions to increment, decrement to the next previous valid index, as mentioned above. You can also use the eachIndex function to iterate over the valid character indices. So you could collect each index of S, and it's a 7-element vector for the integer 64 types. Cool. And so those are the indices of each character. Very nice. And then to access the raw code units, bytes for UTF-8 of the encoding, you can use the code unit s, I function, where the index I runs consecutively from 1 to encode units s. The code units s function returns an abstract vector wrapper that lets you access the raw code unit bytes as an array. Okay. So letting us know about some conventions with Julia allows for invalid UTF-8 code unit sequences. I'm going to skip over that just because it's a little in the weeds. In particular, that means that overlong and too high code unit sequences and prefixes thereof are treated as single invalid character rather than multiple invalid characters. It's kind of a dull example. I'm going to skip that. Apologies. Let's move right along to concatenation. So let me add another markdown cell. Concatenation. So one of the most common and useful string operations is concatenation. So let's do greet equals hello. Whom equals world. And then string greet. Whom new line. Nice. It's important to be aware of potentially dangerous situations such as concatenation of invalid UTF-8 strings. The resulting string may contain different characters than the input strings, and its number of characters may be lower than the sum of numbers of characters of the concatenated strings. Okay. But that can only happen for invalid UTF-8 strings. And so for valid UTF-8 strings, concatenation preserves all characters in strings and additivity of string lengths. You can also use the asterisk operator to do string concatenation. So you would do like greet asterisk asterisk hello Alex. Nice. And while the asterisk may seem like a surprising choice to users of languages that provide plus for string concatenation, this use of asterisk has precedent in mathematics, particularly in abstract algebra. And so in mathematics, plus usually denotes a commutative operation, where the order of the operands does not matter. An example of this is matrix addition. In contrast, the asterisk operator typically denotes a non-commutative operation where the order of the operands does matter. An example of this is matrix multiplication. So more precisely, the set, and so as such, asterisk is a more natural choice for an infix string concatenation operator consistent with common mathematical usage. So like the order matters, non-commutativity. Okay, that was basically it for concatenation. Nice. Interpolation. Let's get a sip of some water. Cool. So you can construct strings using concatenation, but that can be bothersome. So you can do interpolation on string literals using the $ operator, and it just saves you a little time. So you could do that. Let's just create a string. Let's do $greet $whom period new line, and there is no whom, it's whom, and you can see how the variables were interpolated into that string, which is nice. And then the shortest complete expression after the $ is taken as the expression whose value is to be interpolated into the string. So, yeah. Both concatenation and string interpolation calls string to convert objects into string form. However, string actually just returns the output of print. So new types should add methods to print or show instead of string. Most non-abstract string objects are converted to strings closely corresponding to how they are entered as literal expressions. So if you take like a vector, 1, 2, 3, and then let's take v, or actually let's print out just what this looks like plain, and then let's do the string with v, and then the $v, and you can see how the computer handles printing out the data differently or representing it differently. And so string is the identity for abstract string and abstract char values. So these are interpolated into strings as themselves, unquoted and unescaped. So if we do something like C equals X, then we can do $C, and you can see now it's a string, literal. And then if you really need to include a dollar into, like the actual $ into your string literal, just escape it with a backslash. So let's do something like backslash $C. And so you can see how I'm interesting. Oh, maybe that's with the print statement only. I was expecting it not to show the backslash. Yeah, there we go. Okay, cool. Now let's move on to another quick section. Triple quoted string literals. So when strings are created using triple quotes, they have some special behavior that can be useful for creating longer blocks of text. So first, triple quoted strings are also dedented to the level of the least indented line. This is useful for dividing or for defining strings within code that is indented. So for example, you could do something like str equals hello world. And actually this should go yeah, that looks about right. And then let's just print that out actually. Cool. In this case, the final empty line before the closing triple double quotes sets the indentation level. The dedentation level is determined as the longest common starting sequence of spaces or tabs in all lines, excluding the line following the opening triple double quote, and lines containing only spaces or tabs. Okay. Here's another example. Let's do triple quote. Let's do a tab, couple. This is a test. Nice. Next, if the opening triple double quotes is followed by a new line, the new line is stripped from the resulting string. So, hello is equivalent to hello. But this will retain that extra line. Nice. But stripping of the new line is performed after the dedentation. Never heard dedentation before. Let's do hello world. Yeah. If the new line is removed using a backslash, the dedentation will be respected as well. So a very long word. Nice. Okay. Trailing white space is left unaltered. Triple quoted string literals can contain a single double quote character without escaping. Note that line breaks in literal strings, whether single or triple quoted, result in a new line LF character /n in the string, even if your editor uses a carriage return to end lines. To include a carriage return in a string, use an explicit escape /r. For example, you can enter the string literal a CRLF line ending /r/n. So let's just do that real quick, and then we'll move on to a new section. A CLRF line ending /r/n. What if we print it out? Print ln. Okay, whatever. Now let's move on to some common operations. We're getting to the home stretch today with Julia. All right, you can lexicographically compare strings using the standard comparison operations. So you can do abracadabra. Is that less than xylophone? Yes. Yes, it is. And then you can search for the index of a particular character using the find first and find last functions. So let's find the first instance of the Y character in xylophone, and I believe it'll be index 2. Yep. And then if there's no such character in the string, I believe it'll return nothing. Yeah. Okay. You can use a cursin function to check if a substring is found within a string. So can we do a cursin phone xylophone? What about does abracadabra occur in xylophone? No. Okay. Nice. Some other useful functions that people might come across in their Julia endeavors include, with strings at least, first index, last index, length, number of code units, code unit, this index, next index, and previous index. All right, so the next section doesn't actually have any code, so I'm not going to create a new block in the notebook, but non-standard string literals are come up sometimes. There's situations when you want to construct a string or use string semantics, but the behavior of the standard string construct is not quite what is needed. Julia provides some non-standard string literals for those cases, and that looks like a regular double-coded string literal, but is immediately prefixed by an identifier and may behave differently from a normal string literal. So regular expressions, byte array literals, and version number literals, as described below, are some examples of non-standard string literals. So users and packages may also define new non-standard string literals. So I guess we are going to have section. That was a bigger section, but I'm just going to denote the smaller sub-nested components. So let's do a markdown cell. We'll call this regular expressions, and let's get into it. So Julia has Perl compatible regular expressions, regexes, as provided by the PCRE library. These expressions are related to strings in two ways. The obvious connection is that regular expressions are used to find regular patterns in strings, and the other connection is that regular expressions are themselves input as strings, which are parsed into a state machine that can be used to efficiently search for patterns in strings, not springs. So let's define a regex pattern. I'm going to copy paste that because I will totally screw that up. There's just too many random characters. Okay. And then type of it just knows it's a regex. Okay. And then to check if a regex matches a string, use occurs in. So let's do occurs in. Oh, the autocomplete finally. So we'll do regex, or no, we'll just call it re, and then not a comment. Okay. So we're looking for one of these oddball characters, not a hashtag. Nice. Okay. So occurs in just returns a true or false, but you actually want to know sometimes whether the string was matched, but also how it was matched. And so to capture this information, you can use the match function instead. So let's do this. Replace occurs in with match. And you can see it matched on the pound sign. If we replace this with a question mark, I would expect it to match on the question mark now. Or actually, no, because that's not defined. Or, yeah, I don't actually know that regex pattern. Invalid syntax. Interesting. Oh, I gotta escape it. That's why. Okay. Interesting. Okay, if the regular expression does not match the given string, match returns nothing, a special value that does not print anything at the interactive prompt. Other than not printing, it is completely normal value, and you can test for it programmatically. And it's just nothing. So that's cool. If a regular expression does not match, the value returned by match is a regex match object. Or if it does match, excuse me. These objects record how the expression matches, including the substring that the pattern matches and any captured substrings. If there are any, okay. This example only captures the portion of the substring that matches, but perhaps we want to capture any non-blank text after the comment character. We could do that like this. So let's do m equals match. And I'm going to copy paste this regex pattern because I'll totally screw that up. And then we'll do hashtag a comment. You can see the regex match returns hashtag a comment. And then the value after the hashtag that was matched is a comment. So that's pretty nifty. You can also extract the following info from a regex match. The entire substring matched, the captured substrings as an array of strings, the offset at which the whole match begins, and the offsets of the captured substrings as a vector. And you access those using just the dot notation as such. For when a capture doesn't match, instead of a substring, m captures contains nothing in that position, and m offsets has a 0 offset. Here's a pair of somewhat contrived examples that we are going to skip because they look pretty contrived. But it's convenient to have captures returned as an array so that one can use destructuring syntax to bind them to local variables. As a convenience, the regex match object implements iterator methods that pass through to the captures field, so you can destructure the match object directly. Okay. And then captures can also be accessed by indexing the regex match object with a number or name of the capture group. This one's a little shorter, so I will do this. A little copy paste because it didn't hurt anyone. So that's our regex match, and now let's index into minute, which is pretty rad. And then we can also do M2, so you have options on how to index into there. Captures can be referenced in a substitution string when using replace by using the \n to refer to the nth capture group and prefixing the substitution string with s. You're able to modify the behavior of regular expressions with some flags, but we're not going to go into that right now because they're a little outside the scope of this lesson. But if you're into regex, go for it. Cool. Next, we're going to move on to byte array literals. So let me create another markdown cell. So this is another useful non-standard string literal. It lets you use string notation to express read-only literal byte arrays. So one such example would be b data xff / u2200 wild. And so you can, there's some overlap between these rules. Since the behavior of /x and octal escapes less than 0x80 are covered by both of the first two rules, but here are these rules agree. And so, yeah, this is kind of like outside the scope of many users, I would say. So don't get too tripped up in this, but yeah, you have this option in Julia. And then another option is the version number literals. And they can be expressed with non-standard string literals of the form v 0, 2, 3. And I'm missing the closing. And there you go. That's a version number. And these follow the specifications of semantic versioning, which is pretty nice. There's also something called a raw string literal. with that, we can return something as such. Println raw. Let's do /////. Nice. And notice that the first two backslashes appear verbatim in the output since they do not precede a quote character. However, the next backslash character escapes the backslash that follows it, and the last backslash escapes a quote, since these backslashes appear before a quote. Nice. So that was our whirlwind tour of strings. On that note, I think this is a healthy stopping point for us today. The next section on functions is another beefy page, so we'll get on that next time. But I just want to thank you for hanging out today, learning with me, and joining our community of tinkerers at the Graph Protocol. So I really look forward to the next session with you, and hope you have a wonderful day. I'm Alex. This has been Code Along with Alex, and see you next time.